Hi again, everyone. So in this video, I will give an overview on solving differential equations using Laplace transforms. It's going to be pretty sweet and exciting. So let's get right into it. So what are Laplace transforms? So here is the definition of what a Laplace transform is. Okay, so it's actually a function whose input is a function and its output would be another function, right? So it's denoted by L of f of t, okay? And its output would be a function in terms of another variable. They call it S, where the Laplace transform is equal to an improper integral, right? Improper integral like this, okay? And then just for future reference, this is how you would define the inverse Laplace transform, okay? Um, Inverse Laplace transform, you just take the function in S and you transform it back into a function in T. So the goal here is we're going to use a Laplace transform to turn a differential equation into an equation that is algebraic, into an equation that has S's in it, and we'll be able to solve for the general solution. Okay. So that is the idea. We're going to transform a differential equation into an algebraic equation in S, right? And then future videos, we're going to show how the inverse Laplace transform is applied to find the general solution for the indicated differential equation. Okay. But for now, let's look at Laplace transforms of various functions. Um, So we want to compute the Laplace transform for the following functions, right? Let's say C, excuse me. So let's compute the Laplace transform for a constant. We can compute the Laplace transform for e to the at and then sine of at, let's say. Okay. So for part A, right? So we're going to look at the Laplace transform of a constant. Okay. And so this equals to the integral from 0 to infinity of c times e to the negative st dt. Okay, so this equals to c times the integral from 0 to infinity of e to the negative st dt. And so this equals to minus c over s e to the negative st. Evaluate from 0 to infinity. Normally you would take the limit as n goes to infinity of this quantity. 0 to n, right? And so this equals to the limit as n goes to infinity of minus c over s times 1 over e to the s times n minus 1, minus 1. Okay? As n gets bigger and bigger, this quantity right here would be 0. And so essentially we'll have c over s. Okay? And that is the indicated Laplace transform of a constant. So it's c over s. Okay? How about e to the at? E to the at. E to the at, where a is a constant. So let me erase this here. So for part B, right, so we're going to look at computing the Laplace transform of e to the at. Okay, so this equals to the integral from 0 to infinity of e to the at times e to the minus st dt. And this equals to the integral from 0 to infinity of e to the a minus s times t dt. And I'm going to rewrite it like this. So the integral from 0 to infinity of e to the minus s minus a times t times dt. Okay? So I'm going to write out like this. And so this equals to minus 1 over s minus a e to the minus s minus a times t. And this goes from 0 to infinity. And this equals to the limit as n goes to infinity of minus 1 over s minus a of minus 1. Okay, so I'll stop here. So there's going to be a couple of cases to look at, right? And that is if the s minus a exponent is positive, or s minus a is a negative number, right? There's a reason why I wrote it out like this. So if s minus a is a negative number, let's say, well, this quantity right here will be positive, right? And so if s minus a is a negative number, we'll essentially have that this integral will diverge. If s minus a is less than 0. Okay, it's less than 0. If, on the other hand, s minus a is positive, okay, that would mean the e to the negative s minus a times t um, is negative. So we have a negative exponent. So what that means is this would converge to 0, from 0 to n here. Okay, and then we'll have a plus 1 over s minus a. Okay, so 1 over s minus a. Okay, so the Laplace transform for e to the at, this would equal to 1 over s minus a if s is greater than a. Okay, s is greater than a. Now, the last transform we can go over is sine of at, right? Sine of at. So let me clear out this work here. So if I clear out this work, and we're going to talk about the Laplace transform for sine of at. Okay, sine of at. Okay, so this equals to the integral from 0 to infinity of sine of at times e to the negative st dt. Okay, so I'm going to call this I. And from here, we're going to do integration by parts. So u would equal to, I'll say, sine of at And then dv is equal to e to the negative st dt. Okay, and then du is equal to a cosine of at, and then v is equal to e to the minus st over s, the negative sign. So I is equal to so minus 1 over s e to the negative st sine of at. So minus v du, so that would be plus 1 over s times the integral from 0 to infinity of, or I should say a over s. Cosine at times e to the negative st dt. Okay, so we do integration by parts again. So u equals cosine of at, and then dv is equal to e to the minus st dt. And so du is equal to negative sine at, and then v is equal to minus e to the negative st over s. Okay, so I equals to minus 1 over s e to the negative st times sine of at plus a over s times minus 1 over s cosine of at, and then positive, but that's still negative. So that's minus the integral from 0 to infinity of, that's minus a. So I'll have a minus a over s out front, and sine of at times e to the negative st dt. Okay? All right. But it turns out we have the same integral as the one we started with, right? So this is I here. So what that means is if I just clear out some of this work, so what that means is, so if I go up here, so I is equal to minus 1 over s times sine at minus a over s squared e minus st cosine of at, and minus a squared over s squared times I. Okay, times I. All right. So don't forget, we need to evaluate our result from 0 to infinity, right? But we can solve for I here, right? And so if we add this quantity to both sides, right? What we'll have is I times e to the negative st sine at minus a over s squared e to the negative st cosine at. Okay, so okay, great. So we know what I is. Okay, what we need to do now is we need to evaluate the right-hand side of this equation from 0 to infinity, right? Now, if we look at the limit as n goes to infinity of s times n times sine of a times n. So if you look at this quantity, excuse me. So this is the upper limit of integration. So we're going to use the squeeze theorem, right? The squeeze theorem. Now, sine and cosine, right? They will always be in between a -1 and +1, right? So you can apply the same logic to cosine, right? So cosine of any angle will always be in between -1 and +1, right? And if I divide both sides by e to the Sn, I'll get this, right? Okay. And just look at the limit of the endpoints, right? This limit is 0 as n gets bigger, right? So this goes to 0 and this goes to 0. So therefore, by the squeeze theorem, this limit will go to 0. Okay. Same idea here, right? Just you want to look at the limit of the endpoints. This will go to 0 as n gets large, and this will go to 0 as n gets large. Therefore, we can conclude that this limit goes to 0 as n gets large. Okay. And so the upper limit would be 0, and then minus the lower limit. Sine of 0 is 0, and cosine of 0 is 1. So the lower limit, this would be 0, and this would be minus a over s squared. So what we can conclude now is, so let me erase this. Okay, so let me erase this part. This is all review in calculus 2, I am hoping, right, with improper integrals. So, so what we have here on the right-hand side and on the left-hand side is I times 1 plus a squared over s squared equals to so that's minus negative, so that would be a positive. So a over s squared. And so what we can conclude here is s squared plus a squared over s squared times I equals, Jesus Christ, a over s squared. Okay, so this integral here, once you evaluate it, this equals to a over s squared plus a squared. So that is the Laplace transform for sine of at. So I'm going to write it down here. So a over s squared plus a squared. And I want you to try figuring out the Laplace transform of cosine at on your own. If you do it right, you should get this quantity, s over s squared plus a squared. Okay, on your own. Okay, but most of the time, we will be using a Laplace transform table. Okay. Let's see. Do I want to go over anything else? Okay. I guess there is one other Laplace transform I want to go over. Yeah, I'll do that. So how about if we have the Laplace transform of let's say y prime of t with an initial condition. Okay, so this is going to be important in the next slide here. But let's actually go over the work on how we would compute that. Um, so we're going to look at how we would compute the Laplace transform of derivative of y of t. Okay, and if we know that an initial condition, right, let's say is y naught, it doesn't have to be zero, but it could be just any other constant, right? So what that means is, so this equals to the integral of y prime of t times e to the negative st dt. Okay. All right. And so eventually we're going to be using integration by parts, right? And so integration by parts. So u is equal to y prime of t, and then dv is e to the minus st. Oh, I'm sorry. It's the other way around. It's the other way around. So this time I'm going to let u equal to e to the negative st. And the dv is y prime of t dt. And so du is equal to minus s e to the negative st dt. V is equal to y of t. Okay. And so this will equal to uv, so y of t times e to the minus st minus, so that would be a plus s times the integral from 0 to infinity of y of t times e to the minus st dt. Okay. And y, so y of t, so y of t is just a function, right? And as t gets bigger, right, e to the minus st would eventually go to 0. And so what you have is the lower limit is y of 0. Okay. Y of 0 times e to the 0, which is 1. And then it will be plus s times the Laplace transform of y of t. Okay. And if I want to look at a second derivative, right? So if I want to look at the second derivative, the pattern would be the same, right? So this is y double prime, y prime, and so what this turns out to be by integration by parts, this would be y prime of t times e to the negative st from 0 to infinity, plus s times the integral from 0 to infinity of y prime of t times e to the negative st dt. Okay. And so this is plus s times, so we computed this already. So this is y of t times e to the minus st from 0 to infinity minus s times the Laplace transform of y of t. Okay. this quantity right here, so as t gets large, right, this quantity as a whole, it would be zero, right? So we'll have zero, so it'll be zero, so it'll be zero minus, if we know a second initial condition, let's say y prime at zero is w zero, let's say, right? So it'll be minus y prime of zero, and then so minus y prime of zero plus um, um, so that middle term here, so that would be zero, and so zero minus, so zero, so it'll be zero minus s times y of zero, and then minus s squared times the Laplace transform of y of t. Okay. Pretty straightforward, right? Um, okay. Um, right. Okay. So that's the Laplace transform for a second derivative of a function, right? And so here's the overview of Laplace transform. So here's some important information that you need to know. So this right here, this is just the table of various Laplace transforms of functions. Um, so we have Laplace transform of a constant, so it could be one or any other number. So C, this is C over S. Okay, e to the at, and then any power on t to the n, now equal to n factorial over s to the n plus 1, and then sine of bt, cosine of bt, t to the n times e to the at, right? And then we'll have e to the at sine of bt and e to the at times cosine of bt. All right, so those are the notable Laplace transforms that you need to know. Okay. The other fact is that the Laplace transform is a linear transformation, right? It's a linear transform. So if f1 and f2 are functions whose Laplace transforms exist, okay, for any value z that's greater than alpha, then this property for sums of Laplace transforms is valid, okay? The Laplace transform of f1 plus f2 is equal to the Laplace transform of f1 plus the Laplace transform of f2, okay? And then the Laplace transform of a constant times a function is equal to a constant times the Laplace transform of f, okay? And the third fact is using Laplace transforms for derivatives of functions, okay? So yeah, this is what we went over. So if f of t is a continuous function and then f prime of t exists and it's piecewise continuous, okay, for every positive value or every non-negative number, okay, then for s greater than alpha, the Laplace transform of f prime is equal to s times the Laplace transform of f and then minus f of zero, right? So usually when you're using Laplace transforms to solve a differential equation, sometimes you're given a initial condition, right, for x equals 0. Okay. And then just to take it a little bit more abstract, this is uh, the derivatives of the Laplace transform. Okay. And so so t to the n, so they're saying the nth derivative of the function of t. Okay, so they're saying the nth derivative, it's not an exponent here. So you alternate sign, so you alternate sign with n, okay, and then the last power, you're just taking the Laplace transform of f of t. Okay. So yeah, so that's important things to know going forward in the next few videos on Laplace transforms. But let's go over some comprehension problems that you will do. These are really simple problems. Usually, you just taking the the improper integral. That's what these problems constitute. So, in the next few videos, we're going to be discussing in detail about Laplace transforms, and then using those to solve any order differential equation. So stay tuned for more fun math. So thanks for watching, and I'll see you next time.